Hello student friends, I'm Dr. Bijay Hazarika. So starting a video is a very important concept, and indeed it's a video where we can find that how the modern physics has been evolved out. For the last few centuries, this idea is really sweeping all our minds, and everyone is very keen to know about, and there's nothing all other than quantum mechanics. So I'll be dealing with this video how the quantum mechanics started its journey and how the conceptions were put forward and basically the things were developed. So it's a very things are made try to be made very simple and easy to understand. And so let's start. So it's basically the classical physics which has been used today in our daily life or whatever be the physical phenomena around us. But thing is that classical physics sometimes fail in certain ideas, and in that case that those failures actually become the pillar of success, and later it made to develop the quantum mechanics. So in classical mechanics, basically it's the Newtonian laws, and then some developments by Lagrangian, Hamiltonian, all these formalisms are there. But however, with those modifications, even though most advanced techniques of the classical mechanics are not being able to explain some of the phenomena. The first one was that the classical mechanics find difficulty in explaining was the number one was stability of Rutherford et al. So according to classical mechanics, that the charges, the electrons revolving around the nucleus would emit electromagnetic radiation, and day by day the energy will decrease, and ultimately it will fall down on the nucleus. That means the atom will be collapsed. But we know that the atom cannot collapse. That's why we are living. So that classical mechanics idea is not being cannot be taken to be granted as far as we to talk about the stability of atom. The second one was that there's some when we see the spectrum of radiation, there are certain things that there are some integer rules are there. Integer rules means that there are some like Rydberg formulas there. Equation number 1.1, where you can see that the frequency is given by some constant, and 1 by n square by 1 minus n square, where n and m are integers. So it's a difference of two integers. So difference of two integers, this cannot be explained with the help of classical things. So this was one of the failure of classical mechanics. Then the third one, the most important one, which really lead to the development of quantum mechanics, blackbody radiation. Blackbody radiation is found to be that for the energy becomes very high, and almost tends to infinity for large frequencies, according to classical explanation for a black body. But however, it is found that it's not the same. So it is also known as ultraviolet catastrophe, and that particular failure of classical mechanics in explaining this energy spectrum of black body is another reason that this quantum mechanics were evolved. Then the photoelectric effect. Photoelectric effect was invented, and they try to find explain the phenomenon. In the photoelectric effect, what happens is that if light strikes a metal surface, then electrons are emitted. Those electrons are known as photoelectrons, and the photoelectrons have certain characteristics like that. It is emitted only when the frequency of the incident radiation is greater than certain frequency known as Tarot frequency, as well as even if a very dim light falls on, but having that particular frequency falls on a metal surface, it can also eject electrons. Whereas a very intense light, even if not having that requisite frequency, cannot reject an photoelectron. So classically, these things are not explainable. So photoelectric effect is one of the things that people could not explain with the help of classical ideas. Then came that number 5th one, small scale particles. Small scale particles means electrons, protons. Those structures cannot be explained. We cannot find those things like their momentum or their position. These kind of things cannot be measured in classical context. This was one of the things, and the accurate determination was never possible. If we can find a position of an electron, then we cannot find a momentum at the same time. So the simultaneous measurement was not possible there. And also, like those microstate systems, number 6, I can say that just like that they have also the same things, that simultaneous measurements is not possible, and even we cannot define their state in terms of classical context. So these 6 particular things that classical theory cannot explain actually compelled us to think that a new thinking is required, and the new thinking, new thinking ultimately became the quantum mechanics. So the idea begins here, and the thing is that if we have a will, we can have a way, and that will was the first will was done by Max Planck, through his famous quantum hypothesis, where he proposed the discreteness of energy. He put forward that energy is not having continuous distribution. It's like some kind of discrete quanta. That means like some packets. So if, for example, here you can see that energy is taking some values like epsilon, twice epsilon, 3 epsilon, dot like that. Where epsilon is nothing but h nu, where h is Planck constant and n is integer 1, 2, 3. So he called this epsilon as quanta of radiation, or simply you can call it as photon. So the energy is nothing but energy is coming in terms of sub-quanta, like maybe 0, maybe h nu, maybe twice h nu, like that. So he found out the expression for black body radiation, the expression 1.2, h nu by e to the power h nu by kT minus 1. So if we put a limit h tends to 0, we get this, and ultimately we get the classical value of kT. KT is the classical value of a black body radiation radiator, and this clearly established that 1.2 is a general expression, and under the special condition h tends to 0, this quantum expression can be converted to classical expression. So thing is that the black body, according to quantum hypothesis, Planck's quantum, the black body actually consists of certain harmonic oscillators having this kind of discrete energies, and they're just like in the microscopic scale, that energy is not a small one, and ultimately his explanation was something that revealed that there's some another truth behind explaining black body radiation, and he was successful in explaining all those things. And here we have some things here. There's some limits like h tends to 0 and n tends to infinity. This means h tends to 0 means Planck constant is almost becoming 0 in the classical scale, and n tends to infinity means that there's some numbers are involved here. Numbers means that integer number. If n is very high, in that case also that quantum results becomes quantum classical results. That is also things. So we have put some examples here. For example, we take simple pendulum. The energy is very small. If we take nu equal to 1 per second, 1 hertz, the energy is 6.6 in 10 to the minus 27 R. But this on the classical is very small. But suppose we take light. So in the case of light, the frequency is 10 to the 10 hertz, and in that case energy is equal to 4 electron volt. That means if we consider light means it's quantum actually. So that means that we when we reach to the quantum level, we have to talk about light or such kind of things like photons. Photon is just a quantum of light. So in that case, our idea of classical mechanics need not to be involved. We can see that quantum mechanically the energy is high, 4 electron volt, which is very high energy, and indeed we can take care of light or some these kind of things as in terms of quantum mechanics. But this is not possible for a classical oscillator having a frequency of 1 per second, which is obvious in this example. Then these are the energy levels that the Planck's oscillator concept. That means that, as Planck pointed out, that the black body has harmony oscillators consist of which emits energy, and that the energies are like this. H nu is the lowest energy, E naught. H nu is the first level of energy. Y H nu is the second level. E2, E3 level. Yeah. So we conclude that we can make a conclusion regarding this quantum hypothesis, that this quantum hypothesis quite well explains the black body radiation, and at the same time it allows us to get back the classical results under certain limits, and it actually put a very strong basis to new idea that the energy is no longer a continuous thing. Energy is a discrete kind of thing. It is a discontinuous kind of thing, and it takes energy values like 0, h nu, twice h nu, like this. So we cannot think that energy is continuous. It's simple. On the same hand, we can make a classical analogy and quantum mechanical analogy, taking a classical oscillator of 1 Hertz frequency, 1 per second, where we find the energy level very low. So there we think that classical expression is quite okay. But in the case of quantum mechanics, that means if we take a light, there we find that the energy is something having value like 4 electron volts. That means that to explain something like related to light, we can have quantum mechanics there. And one important thing is that h tends to 0. That means that it's a classical value of h, we can say. That means that in the classical concept, the value of h is very small. It's almost 0. But in quantum mechanics, although its value is 6.6 into 10 to minus 34 joules second, but it's quite large in quantum mechanical scale. And this is one thing. And also another thing is that n tends to infinity. N means that the integer, that the energy levels, that this n is actually within the energy levels. If the energy levels are very high, then also we get back the classical results. So these conclusions are actually made through a statement, the Bohr's correspondence principle. So the Bohr's correspondence principle actually consists of 2 parts. The first one is that the prediction of quantum theory coincide with those of classical analog for large quantum number. This is what we have already stated. N tends to infinity means that quantum mechanics becomes classical mechanics. That's number 1. Number 2 is that the selection rule for energy changes are same both in quantum theory and classical theory for large quantum number. So there's some selection rules we are discussing about spectral lines in Bohr theory, and those selection rules, maybe the selection rule regarding this n is actually known to be principal quantum number, is actually nothing but it's the same rules to be considered. That means that n value may be changing like plus minus 1, plus minus 2, like that. So regarding Bohr's correspondence principle, is quite clear that if n tends to infinity, that our quantum mechanical expressions become classical expressions. So we can have an example for this, the mathematical part. So this results, this f is actually the value of this. We can say that classically we calculate the frequency revolution in an atom classically, and that is given by this equation 1.6. And when we use the Planck's idea, then we get the expression like 1.8. And you can see the expressions. And if we put that this n is very larger than del n, then ultimately this frequency is new frequency is going to be 1.9, equation 1.9. We can make a comparison between 1.9 and 1.6. You see here f is representing frequency also, it's classical frequency, and nu is representing quantum frequency. Now if you put del n equal to 1, only 1, then we can see that this expression and this expression are same, because del 1 is equal to 1 means it is 2 by n cube, it is also 2 by n cube, and similarly here e1 by n, e1 by h. So 1.9 and 1.6 are same, only thing is that we have to put a selection rule, del n is equal to 1. So Bohr has successfully demonstrated that for large quantum number, the condition is here, n is very larger than del n, for large quantum number, the NF is very large, Ni and F are very large. That means the quantum numbers are very large quantum numbers. In that sense, the classical expressions and quantum expressions for frequency don't have any kind of distinction. They are all same. Only thing they put a condition of selection on del n equal to 0. So it is success. You can say that quantum mechanics is nothing, but it's just classical mechanics is nothing, but it's just the special case of quantum mechanics. Only thing is that we put a condition h tends to 0, quantum mechanics become classical mechanics. We put n tends to infinity, quantum mechanics become classical mechanics. So in that sense, quantum mechanics is a more generalized idea over classical mechanics. Classical mechanics cannot take account of all these things that quantum mechanics can take account. So that's what Bohr's correspondence principle, that quantum mechanics turning into classical mechanics. So Bohr's correspondence principle is one of the pioneering theory where one can establish that quantum mechanics can be converted back to classical mechanics. This video is ending here. Keep watching our new videos and don't forget to comment on that and put suggestions. Thank you very much for watching the video.